Hello. In this lesson, we will begin by solving some problems using the gas laws that we developed in the previous class. Now, for that, you got to recall some of the equations that we developed. Now, do you remember the universal gas equation? All right, let's have a look at that to begin with. We have PV equal to nRT. What are these quantities? P is the pressure, volume, V is the volume, N is the number of moles of the gas, R is the universal gas constant, and T is the temperature in Kelvin. And remember, the value of R depends on the units for measuring pressure and volume. When pressure is measured in Pascal, the value of R will be 8.314. Is that right? Yes. And if pressure and volume are measured in atmosphere and liters, you must use the other value of R. Alright, let's start with the first problem. That is example 4. We have done 3 problems already. A gas is kept at a constant pressure. Pressure remains a constant. If the temperature is changed from 50 degrees Celsius to 100 degrees Celsius, by what factor does the volume change? The pressure remains a constant. Well, we don't need the universal gas law there. When pressure remains a constant, what do we have? We have the Charles law. Is that right? What does it say? Volume is directly proportional to temperature. So let's write down the temperature. T is 50 degrees Celsius, but we need that in Kelvin. So add 273 to this. 323 Kelvin. And what is T3? T3 is 100 degrees Celsius, and that is 373 Kelvin. When the pressure is constant, what is the equation we have? V over T is a constant. Volume is directly proportional to the Kelvin temperature. Now, what does this mean, V over T is a constant? It means that if V1 and T1 are the volume and temperature in state 1, and if V1 changes to V2 when temperature T1 changes to T2 in state 2, what will this equation then lead us to? It will give us V1 divided by T1 equal to V2 divided by T2. That's right. This is what this leads us to. Alright, we know T1 and T2, therefore what are we supposed to find? What factor does the volume change? We want a relation between initial volume and final volume. Or the question is, the final volume is what part of the initial volume? Alright, so we would write it like this, V2 over V1 equal to, is that right? V2 over V1 equal to T2 over T1. And T2 over T1 is 373 over 323. That is 1.15. Now what that means is V2 equal to 1.15 times V1. Is that right? The final volume is 1.15 times V1, and that's what this is expected us to do. Okay, let's move on to the next problem. Example 5. A 10-liter vessel contains gas at a temperature of 0 degrees Celsius and a pressure of 4 atmosphere. How many moles of gas are there in the vessel? Well, what is the equation that contains the number of moles? Obviously, we need to go there. What else? How many moles of gas are there? How many molecules are there in the gas? Well, how many of you remember the number of molecules in 1 mole? Well, you remember the concept of Avogadro number. 6.023 times 10 to the 23 molecules per mole. So if you know the number of moles, then you know the number of molecules. Okay, let's pick the data here. What do we have? V equal to 10 liters. The temperature T is 273 Kelvin, 0 degrees Celsius. Pressure P equal to 4 atmosphere. Well, you need to convert. Well, you can leave the pressure at 4 atmosphere as long as you use the value of R corresponding to that. The value of R is 0.08206 liter atmosphere per mole Kelvin when the pressure is measured in atmosphere, volume is measured in liters, the temperature in Kelvin, and so on. So don't forget that. Okay, PV equal to nRT. We know P, we know V, we know T, and we know R. Therefore, N equal to PV over RT. Now use all those values. Look at the units that we use. P is 4 atmosphere, V is 10 liter, R is 0.08206 liter atmosphere per mole per Kelvin, and temperature is 273 Kelvin. Look at how the units can be managed. Let me go to the whiteboard. Now, watch this. Liter and liter will cancel. Atmosphere, atmosphere will cancel. And look at the denominator. Per Kelvin cancels with Kelvin. And per mole will go up to become moles. So, N measured in moles will be your units. And what does that give you? To calculate that, I told you that you must do these calculations along with me. That gives you 1.79 moles. Now, how many molecules are there? Each molecule contains Avogadro number of molecules. Each mole contains Avogadro number of molecules, 6.03 times 10 to the 23. And therefore, how many molecules are there in these many moles? What do? The number of moles multiplied by the number of moles multiplied by the number of molecules per mole, and that gives you 1.08 times 10 to the 24 molecules. Okay, let's move on to another problem. Example 6. A room is 6 meter by 5 meter by 3 meter. Part A. If air pressure in the room is 1 atmosphere and the temperature is 300 Kelvin, find the number of moles of air in the room. B. If the temperature rises by 5 Kelvin and the pressure remains a constant, how many moles of air leave the room? Alright, what do we need to find first? Find the number of moles of air in the room. Now, what are the information you need to find the number of moles of air? We need the pressure. Do we have the pressure? Yes, 1 atmosphere. You need the volume. Can you find the volume? You're given the length, width, and the height. We can find the volume. Alright, we're going to get that in liters. So, pressure in atmosphere, volume in liters, and then you know the value of R. Do we know the temperature? Well, the temperature is there, and therefore you can find the number of moles of gas. Let's write down the data. Pressure is 1 atmosphere, temperature is 300 Kelvin, value of R. Always remember, you need to choose the appropriate value. When pressure in atmosphere and volume in liters, R is 0.08206 liter atmosphere per mole Kelvin. And volume of the air in the room is length times width times height, and that is 90 meter cube. Now, how many of you know how to convert a meter cube to liters? How many liters are there in a meter cube? Well, I don't know. Can I show that to you? Well, watch here. What is a liter? 1 liter is 1000 centimeter cube. And you know that 1 meter cube. 1 meter cube is how many centimeter cube? It is 100 centimeter times 100 centimeter times 100 centimeter. That is 10 to the power 6 centimeter cube. Now tell me, 1 liter is 1000 centimeter cube, and 1 meter cube is 10 to the power 6 centimeter cube. Therefore, 1 meter cube is how many liters? I want you to tell me that. Okay, I'm going to leave that for you. I will give you that value directly. Alright, so 1 meter cube is 10 to the power of 3 liters. So 90 meter cube is 9 times 10 to the 4 liters. Okay, now we use all these values. N equal to PV divided by RT. And use all those values. P is 1 atmosphere. V is 9 times 10 to the 4 liters. R is so many liter atmosphere per mole per Kelvin. Temperature is 300 Kelvin. Well, I have a small problem there. Have you noticed that? It is 300 Kelvin, not per Kelvin. So you must take that off. Okay, now what does that give you? That's equal to 3,656 moles of air are in the room. And now, the temperature rises by 5 Kelvin and the pressure remains a constant. So, what all we have in the new situation, the pressure remains a constant, volume will not change, the room cannot change volume, R will not change, but the temperature now changes by 5 Kelvin. It becomes 305. Therefore, how many moles of air are there in the room now? Let's go to the next slide. So, when the temperature rises by 5 Kelvin, the new temperature is 305 Kelvin. Again, you notice I've been cutting and pasting, and so I repeated the same mistake. So, cut that off. That must be Kelvin, not per Kelvin. And what does that give you? 3,596 moles are left now. Now, you know the number of moles previously. You know the number of moles at a higher temperature. That means some air has left the room. How many moles have left? Is 3,656 minus 3,596. 60 moles of air left the room when the temperature rose by 5 Kelvin. Alright, let's move on. One more example. A container with a volume of 6 liters holds 10 grams of liquid helium. As the container warms to room temperature of 20 degrees Celsius, what is the pressure exerted by the gas on its walls? Okay, what do we have? Let's pick the data. Volume is 6 liters. Mass is 10 grams. Now, where do we use the mass? Well, since we know the molar mass of helium, anybody tell me what is the molar mass of helium? If you know the molar mass of helium, we can find the number of moles in 10 grams. That's what we're going to do. The temperature is 293 Kelvin. That's the room temperature. And the value of R we're going to use is again in liter atmosphere per mole Kelvin, which means the volume must be in liters, the pressure must be in atmosphere, and so on. Since the molecular weight of helium is 4, that means 1 mole of helium contains 4 grams. That's the meaning. Molecular weight is 4. 4 grams of helium makes up 1 mole. So 1 mole of helium has a mass of 4 grams. Therefore, how many moles are contained in 10 grams? Now you must be able to look at the periodic chart and get the molecular weight of every substance. So if I give you the mass of a sample, you must be able to figure out the number of moles from there. So we got 2.5 moles in 10 grams, is that right? Because 4 grams make up 1 mole, 10 grams make up 2.5 moles. Alright, we have PV equal to nRT, and we are looking for the pressure. Therefore, pressure equal to nRT over V. We have all these values. N is 2.5 moles. R we know, here we are. T we know. V we know in liters. Now, therefore, if you use this value of R and this V in liters, what will be the unit of pressure that we get? The unit of pressure we will get will be in atmospheres. So, put all those and try and cancel the units and see whether you will get atmospheres. You will see liter and liter will cancel. Mole times per mole will cancel. Kelvin times per Kelvin will cancel, leaving us atmosphere as the unit. So the pressure of the gas inside is 10.12 atmospheres. I think we've done a fairly good spectrum of problems, and you must be able to do any problems of this type. Alright, let's now talk about kinetic theory of gases. What does kinetic mean? Kinetic is related to motion. Now, kinetic theory of gases, the theory of gases that is based on molecular motion. Now, one thing I want you to understand and appreciate in this lesson is the fact that physicists, in trying to explain the nature of the world around, we start by looking at situations and forming hypotheses. We want to describe the behavior of gases. Therefore, we start by saying that, well, a gas must be made up of tiny particles that are in a free state of motion. And based on that assumption, we will build up a theory. And the theory can then be applied to situations and see how well they fit the situation. If they fit well, we can conclude that the theory is a good theory. If they don't fit, we will be able to come back and change our hypothesis. You see, that's the way scientific method works. Almost everything in science works that way. So let's look at kinetic theory of gases. Kinetic theory of gases makes the following assumptions. Now look at the way a theory beginning to take shape. A theory always starts with some basic assumptions. What are the basic assumptions we're going to make? Assumption number 1. A gas is made up of identical spherical molecules which are in a state of random motion. So, molecules are in a state of random motion. You cannot determine which way it's going to move. And the motion of these molecules obey Newton's laws of motion. Can you recall some of those motions, especially the second law? What does the second law say? The second law says the net force on an object produces on it an acceleration, so that F equal to ma. And we also said the rate of change of momentum Can anybody complete that for me? What is the rate of change of momentum of a moving object? Well, momentum will not change without a net force. So, rate of change of momentum is a measure of the net force. You're going to use that here. What's our assumption number 2? The volume occupied by the molecules is negligible compared to the volume of the container. If you look at this room, now there are millions, trillions of molecules in this room. But if you calculate the total volume of all the molecules, it will be only a minute fraction of the total volume of the room. Is it right? Well, we are going to work on that assumption. And we build a theory. And if that theory doesn't stand the test, then we will come back and change our assumptions. What is our assumption number 3? The molecules undergo elastic collisions with one another and with the walls of the container, and the pressure exerted by a gas is due to the collisions of these molecules with the walls of the container. Well, obviously, when they are moving at random, sometimes they will collide with each other. They will also collide with the walls of the container. We're going to use that concept actually to build a theory. Is that right? And the pressure exerted by wall is due to the collisions of the molecules on the walls of the container. And finally, a 4th assumption. Forces between molecules are negligible except during a collision. Now, we would assume that if there are few things that are scattered around, there are forces that act among them. Now, here we assume that these molecules exert no forces at all. In other words, intermolecular forces is absolutely 0. That's our assumption. Well, that may be a wrong assumption, but, well, it will not cause a lot of problems for us. Okay, let's now try and use these assumptions to build a theory. Now, let me see if I can take you to a website and show you. Now, watch the way the molecules behave. Here I have a container, and the molecules are in a state of random motion. They hit against each other and also against the walls of the container, and the pressure exerted by a gas is due to the collision of these molecules against the walls of the container. And you can see, if you put all these molecules together, they are a very small part of the total volume. So all the 4 assumptions of kinetic theory are actually illustrated here. Now, what is the 4th assumption? There is virtually no intermolecular forces. And also we said all collisions are elastic. Now, what is an elastic collision? An elastic collision is a type of collision where energy is conserved. Kinetic energy is conserved. Energy is not lost during collision. Alright, now what does this indicate? That shows how each molecule is the distribution of the velocity. Do you think each of these molecules or all the molecules have the same velocity? No. The velocity of these molecules are random and they keep changing. You see, when they hit against each other, they can exchange velocities in spite of the fact that the kinetic energy is conserved. So here it shows the velocities of individual molecules can change. That's the distribution of velocities. And that is almost a uniform distribution. Well, is that right? A normal distribution there. So one thing you should know, the velocities of these molecules are not the same, and we will use that in our theoretical part. Okay, let me close this and let's try and build our theory. Now, these assumptions can be used to obtain an expression for the pressure exerted by a gas. Here I have a small container and there are molecules that have their velocities in all directions. Alright? The figure shows a box that contains a gas. It is in a state of pressure P, temperature T, and the volume is V. Let there be n molecules in the box. So look at that. Keep these as we go on, this information. N is the total number of molecules, and each molecule has a mass m. And we will assume that because it is the same type of gas, m is the same for all molecules. Alright. And the velocity, the average velocity of a molecule we call v bar. We said the velocities of molecules actually differ. And v bar is the average velocity of a molecule. Alright? Since the velocity is in any random direction, we assume that v sub x is the average x component of its velocity. Now remember, a molecule can move in the x, y, or z direction, or in any arbitrary direction. So at any time, a molecular velocity has an x component, a y component, and a z component. So let's concentrate on the x motion. Vx is the average x velocity of that molecule. Is that right? Okay. If V is the volume of the box, the number of molecules per unit volume. You see, the N is the total number of molecules that are contained in a volume V. Therefore, what is the number of molecules per unit volume? It will be N over V. So the number of molecules per unit volume is N over V. Let A be the area of the side of the box. This area is A. Alright. When molecules have elastic collision with this wall, they just reverse their velocity. Have you ever tried throwing a basketball onto a wall exactly at right angles? What happens? That ball will be reflected back exactly the same way, almost with the same velocity. And if the collision is elastic, the velocity of impact will be the same and opposite, will be equal and opposite to the velocity of rebound. Now that's what we assume here. The molecules have elastic collisions with the wall and they just reverse their velocity. So let's take one molecule which has an x velocity Vx. What is the momentum of the molecule in the x direction? The momentum is mass times its velocity in the x direction, mvx. Now tell me. Now this is the molecule. This is going to hit the wall with a momentum mvx and is going to rebound. What will be its velocity of rebound? Will be negative vx. So what will be the momentum of rebound? Now, will it be negative mvx? That's right. The momentum of the molecule after collision will be negative mvx. Now tell me, what is the change in momentum? The change in momentum. Alright? Be careful here. Change in momentum is mvx minus negative mvx. When you subtract a negative, it becomes positive. So mvx minus negative mvx is 2mvx. And look at the way I represent the change in momentum, delta px. So, change in momentum is 2mvx. Is that right? If you consider a time interval delta t, all the molecules in the volume A Vx delta t will reach the area in that time interval if all the molecules travel in the positive x direction. Well, did you understand that? Let me see if I can make it clear to you. And that is, You know that if the velocity is Vx, means if a molecule is here and the wall is there, in 1 second this molecule will reach there. That means in 1 second all the molecules in this space. Is that right? Now, if this molecule will reach the wall in 1 second, now that means all the molecules in this volume will actually be reaching that wall in 1 second. Is that right? Because if this reaches, everything else in front of it will also reach. So all the molecules in this volume will reach the wall in 1 second. And therefore, what is that volume? That volume will be, this is Vx, and the area is A, so that will be Vx multiplied by A. But we are not taking 1 second, we are taking a small interval delta t. Therefore, if this is the small interval delta t, then all the molecules in this volume will reach the wall in that interval. And that volume will be, A multiplied by Vx multiplied by delta t. So all the molecules in the volume A, Vx, delta t will reach that area A in that time interval delta t. Okay. And that's an important information. But at any given time, only half the number of molecules are likely to travel in the positive x direction. Look at the way we are using statistics here. You see, we assume that this molecule is moving in the positive x direction. But a molecule is equally likely to travel in the negative x direction. So, the assumption we make is at any given time, only half the number of molecules are likely to travel in the positive direction, the other half going in the negative direction. Therefore, what is the number of molecules reaching the area A in delta t? In that time delta t. All the molecules in this region, if all the molecules reach, then we say all of them are moving to the right. And therefore, our assumption is half the number of molecules in this volume. Now, I'm going to write a step, but that's going to be including a lot of other steps. Tell me, what is the number of molecules per unit volume we obtain? The number of molecules per unit volume is N over V. Now, if you multiply this volume with N over V, that will give you the number of molecules in that volume. So, what is the total number of molecules reaching that area A in that time delta t? Look at this. 1/2. Why 1/2? Because only 1/2 of the molecules are likely to travel in the positive x direction. N over V is the number of molecules per unit volume. And A Vx delta t is the volume there. So this is the total number of molecules that are likely to reach that wall in that time delta t. And each of these molecules will undergo a change in momentum by how much? If you remember, 2mvx. So what is the total change in momentum of all these molecules? The change in momentum of each molecule is 2mvx. So if you multiply these number of molecules by 2mvx, the total number of molecules reaching the area A multiplied by the change in momentum per molecule, and you can see the 2 and the 2 cancels, N over V A M Vx squared times delta t. This is the change in momentum of all the molecules reaching the wall A in a small interval delta t. And therefore, now tell me, what is the rate of change of momentum? The rate of change of momentum is delta px divided by delta t. Let's do that in the next slide. The rate of change of momentum of these molecules is delta px divided by delta t, and that is n over v am vx squared. Well, in the beginning I told you Newton's second law relates the rate of change of momentum to the net force. Is that right? So the rate of change of momentum of the molecules that reach the area A is a measure of the net force exerted by these molecules on the wall. Is that right? Now, according to Newton's second law, this rate of change of momentum is a measure of the force exerted by the molecules on the wall. Now, if Fx is the force exerted on the area A by the molecules, then this quantity will be equal to Fx. So we say Fx equal to n over v am vx squared. Alright. Can you use this and give me an expression for the pressure exerted by these molecules on the wall? Alright. How many of you know what pressure is? How is force related to pressure? Well, pressure is force per unit area. If you divide this force by area, you get pressure. So pressure exerted by the gas is F over A, and that will be therefore N over V m Vx squared. We have now obtained an expression for the pressure exerted by a certain amount of gas enclosed in a container. Is that right? Look at the way, look at the way the theory has been developed using our basic assumptions. Alright, let's move on. So P, the pressure equal to N over V m Vx squared. That means P times V equal to Nm Vx squared. Well, does it ring any bell for you? P times V, if you want to go back into your gas law, you can actually now relate what we obtained here. Now, this equation is based on our assumptions. But we know the universal gas law PV equal to nRT is an established law. We can now compare and see how well we have done. But PV equal to NNAKT. Now, do you remember that one? Okay, let's see if you remember. We said K times Na. What does K stand for here? We talked about that about a class before. K is the Boltzmann constant and Na is the Avogadro number. Therefore, Na times K is the universal gas constant. So PV equal to nRT is the same as PV equal to NNAKT. Alright. Now, what is this? N times Na. N is the number of moles. Na is the number of molecules per mole. Therefore, what does N times Na give you? The total number of molecules. Is that right? So, we got PV, therefore, equal to NKT. What does that lead us to? Let's see. This is leading us on to very interesting territory. So, what we have now is NKT equal to, I'm equating here, we know that PV equal to Nm Vx squared from our assumptions. This is from our assumptions. And this is from the universal gas law, PV equal to NKT. So we will take this result, NKT, and set it equal to Nm Vx squared. Alright, you can see N and N will cancel from both sides. And what does it give you? KT equal to mVx squared. Well, you know that kinetic energy of a molecule is 1/2 mv squared. Now, does it resonate with our definition of temperature? What is the definition of temperature we started with in our last lesson? Temperature of an object is proportional to the average kinetic energy of the molecules. Look at this. Temperature is proportional to the average kinetic energy. I can write this actually in terms of that. Let me show that to you. Now, I can now write, if I divide both sides by K, I have T equal to mvx squared over K, and I can then say 1 over K is a constant, or I can say temperature is proportional to the kinetic energy. This big K stands for kinetic energy. You see, the temperature is, what is missing here is a 1/2, which is a constant. So I can put it all together and say the temperature is proportional to the kinetic energy. That is a neat way, and our assumptions fit very well in what we see here. So you can see 1/2 kT, I multiplied now both sides with 1/2 to obtain that result. Average kinetic energy due to the x motion of the molecule, therefore, is 1/2 kT. A very important result. The average motion due to the x motion is 1/2 kT. Therefore, what will be the average kinetic energy due to the y motion? It will be also 1/2 kT. What will be the average kinetic energy due to the z motion? It will be also 1/2 kT. So, if average energy due to x motion is 1/2 kT, but the molecule is equally likely to move in the x, y, and z directions. Therefore, Vx squared can be approximated as 1/3 of the square of the actual velocity. Does it make sense? If the actual velocity is, say, v bar, you remember we started, then v bar can be considered to be 1/3 of the square root of that. Now, how do I write it? If v bar is the average velocity of the molecule, then I'll say Vx squared is 1/3 of v bar squared. Why? Because a molecule is likely to travel in all three directions. Therefore, Vx squared is only 1/3 of the actual velocity squared. Okay, so when we have Vx squared, we can now replace with 1/3 v bar squared. What does v bar now stand for? V bar now stands for the average velocity of a molecule in the whole system. And that's an important concept. We actually call it the root mean square velocity. The average kinetic energy of a molecule is given by K average equal to 1/2 mv bar squared. Now, this 1/2 mv bar squared, look at the way I'm going to write it. It is 1/2 times m times v bar squared. This v bar squared is 3vx squared. Alright? And that will be, if you come back here, 3vx squared. I'm going to take this 3 over 2. Look at that. This 3 came out, became 3 over 2. And mvx squared, mvx squared is what? If you take away this 1/2, mvx squared equal to kt. So I took that 3 out and put it there and replaced mv squared by kt. And very important result. The average kinetic energy of a molecule is 3 over 2 kT. We will use this as we go on. The total translational kinetic energy of n molecules of a gas containing n molecules. We got n moles containing n molecules will be therefore, if 3 over 2 kT is the average kinetic energy per molecule, multiply that by the total number of molecules. It'll give me the total kinetic energy. The total kinetic energy of n molecules of a gas is 3/2 nkt. And I'm going to write it as 3/2 nRT. I'm going to leave for you to figure it out. Well, I'll give you a clue. The total number of molecules n is the number of moles times the Avogadro number Na. And Na times K becomes R. So 3/2 nkt is the same as 3/2 small n RT, the number of moles, and so on. So, the total translational kinetic energy of n moles of a gas is 3/2 nRT. These are very important results which earned PhDs to many people about 200 years ago. Total translational kinetic energy is 3/2 nRT. If n total is the mass of n molecules, then we have 1/2 m total V bar squared. You see that? The total kinetic energy of the gas can now be written as 1/2 total mass of the gas multiplied by the average velocity of the molecules. 1/2 m total V bar squared is 3/2 nRT. And can you solve for V bar from there? You can see these 2's will cancel. V bar squared is 3 nRT over m total. That will be 3 RT over, look at the way I wrote it. The n on the numerator, I brought it down, m total over n. Actually, this n can go up to the numerator. But I wrote it like this. Anybody tell me what is the significance of total mass of molecules in a container divided by the number of moles in that container? Well, this is the molar mass, the mass per 1 mole. So that will be 3 RT over big M, where big M is the molar mass of the gas. And you know the molar mass of any gas can be obtained from the periodic chart. And so, look at this, V bar squared equal to 3 RT over M, the molar mass. Therefore, V bar, what do you call this V bar? The root mean square velocity, equal to square root of 3 RT over M. And if you notice, M is a constant for a given gas, R is a constant. Therefore, the average velocity of the molecules of a gas depends only on the temperature. Isn't that what we started with? Definition of temperature? Temperature is directly proportional to the kinetic energy, average kinetic energy of a molecule. Alright, keep that equation with you. That's an important equation. V bar is called the root mean squared velocity of the molecules. So we normally write V bar as V RMS, RMS, root mean squared. Alright, so what is V RMS equal to? V RMS is square root of 3 RT over M. And look at the way we have been coming from the beginning of this lesson. Simple assumptions led us to very concrete theories. And if we will be applying these as we move on, and if there is any discrepancy between experimental results and these, we will have to come back and change our assumptions. You see, that's the way a scientific principle or a scientific method works. Science has been working like this for hundreds of years. And that will be the way it will work in the future. That's the problem. Find the total translational kinetic energy of 1 liter of oxygen gas held at a temperature of 0 degrees Celsius and a pressure of 1 atmosphere. What is the RMS speed of the oxygen molecule at this temperature? Well, pick out the data. Volume is 1 liter, that is 10 to the power of -3 meter cube. Temperature is 273 Kelvin. Pressure is 1 atmosphere. And this time, I'm going to write that in Pascal. Now, 1 atmosphere is 1.01 times 10 to the power of 5. That's a small mistake there. You must read like this. 10 to the power of 5. Like this. Alright, make that change. Alright, let's use this data to do what? Total translational kinetic energy of n moles of a gas. Anybody tell me what's the relation we just obtained earlier? The total kinetic energy is 3/2 nRT, where n is the number of moles. 3/2 nRT. We don't have n, do we? We have R. When pressure is measured in Pascal and volume is measured in meter cube, then what is the value of R? 8.314 times, well, 8.314 joules per mole per Kelvin. Well, we know R, we know T, but we don't know N. Well, why did I use the red color there? You know, nRT equal to PV, PV equal to nRT. Since we don't know N, but we know P and V, let's write nRT equal to PV. So the total translational kinetic energy is 3/2 PV. And now you see why the unit has to be volume in meter cube and pressure in Pascal. So pressure in Pascal, volume in meter cube gives you the kinetic energy in joules. Alright, that is 151.5 joules. We found the total translational kinetic energy. What is the RMS speed of the oxygen molecule at this temperature? What is the equation for V RMS? And in order to do that, you need the molar mass of oxygen. Does anybody know what the molar mass of oxygen is? Look in your periodic table. You can see 32 grams of oxygen is a mole. So molar mass of oxygen is 32 grams, and write that in kilogram, 0.032 kilogram. So V RMS is square root of 3RT over M. M is the molar mass. R we know, T we know, M we know. So put all those values in there. Now, watch this. I want you to look at the units and tell me, will these units lead us to, what should be the unit we expect? Meter per second. I want you to check that and tell me whether you got that right. Okay? Let me know. And that's equal to 461.3 meter per second is the root mean squared velocity of oxygen molecules at that temperature. Alright, let's do another one. In a period of 1 second, 5 times 10 to the 23 nitrogen molecules strike a wall with an area of 8 centimeters squared. If the average velocity of the molecules is 300 meters per second and strike the wall head-on in a perfectly elastic collision, what is the pressure exerted on the wall? The mass of nitrogen molecules is 4.68 times 10 to the negative 28 kilogram. It's a direct application of what we did. Alright? We got N, the total number of molecules is 5 times 10 to the power of 23. The average velocity, V average, is 300 meters per second. The mass of one molecule is 4.68 times 10 to the negative 28 kilogram. And the area on which these molecules hit is 8 times 10 to the negative 4 meters squared. Now the change in momentum of one molecule due to collision, anybody remembers? It'll be 2mvx. We know this Vx stands for this average velocity. We know m, therefore that will be 2 times m times, that's m, Vx is this. I haven't put the units there, but that will be 2.81 times 10 to the negative 25 Newton second change in momentum. Alright? Now, change in momentum of all these molecules. The change in momentum of one molecule is this. And there are altogether these many molecules. So what is the total change in momentum of all these molecules? Well, multiply the number of molecules with the change in momentum per molecule. And that's the delta P, the change in momentum, is 0.1404 Newton second. What is it that we're looking for? What is the pressure exerted by the wall? What is the definition of pressure? Well, the rate of change of momentum. This change in momentum occurred during a time 1 second. Therefore, what is the rate of change of momentum? Is delta P divided by delta T. This divided by that, and you can see the second and second goes. Therefore, the rate of change of momentum is 0.1404 Newton. Rate of change of momentum is a measure of the force. Now, this is a measure of the force acting on the wall. And how do we get pressure from here? Pressure is force divided by area. So that's the force, and this is the given area. And that's therefore 175.5 Newton per meter square. Well, I think we had a good discussion on kinetic theory of matter, and I think that's about what